So you remember last time there was one thing which I was going to present and somehow I had to postpone it. I will be very short about this, very brief. So it is about the formula which was called in my time Campbell-Hausdorff formula, then it became Campbell-Hausdorff-Baker, or Campbell-Baker-Hausdorff, I don't remember formula. Actually, it was written by Dinkin in his student work in the year of 47. Dinkin now is professor emeritus in Cornell. So I attended his seminar. It was beautiful when I was doing myself. Good. So first, what we want to do. We want to do the following. We have a Lie algebra. We have a Lie group G. Oh, something here. Extreme points. There will be some extreme points, yes, but not this. We have a Lie group G, and we have this dimensional map, of which Lie algebra I can write it G. Into G. And locally it is invertible, it is diffeomorphism of some neighborhood of 0 into some neighborhood of the identity element. Now, we know from by other reasons that the multiplication in G is determined by the commutator in Lie algebra, and it is a very strange fact because almost by nothing, by something which has differential order 2. Now, how to express the multiplication in G in terms of this commutator? We do the following. We take two elements, say Xi and eta in G. We apply the expansion map to them. These are elements of the group, so we can multiply them. And if Xi and eta are sufficiently close to 0, then actually this product will be again in the domain where the exponential map is invertible, and I can apply this. Again, this will be an element of the Lie algebra, and the normal notation is Xi circle eta. So such a local multiplication in the Lie algebra, which corresponds to, which actually gives you the local group structure in the group G, if you identify the two things by means of the exponential map. This operation in the Lie algebra, not bilinear anymore, this operation in the Lie algebra, according to our belief, is fully determined by the commutator. And this is the reason of existence of this Campbell-Baker-Hausdorff formula, that we want to write an explicit expression for this. What we can expect that there will be a series, because it should be defined only locally. So the expression should involve some limit which can exist or not, and this is actually a series. Many people tried to do this. There were formulas, but the formula which can be called explicit, if you don't expect too much of it, was written by, as I said, by Dinkin in the year of 47. And what I'm going to do now, I don't remember it. I want to write on the board, and I hope that this part of the board will be sufficient for this. So the formula is now the sum with respect to, well, first m, which is greater than 0, and second, the sequence of numbers p1, pm, q1, qm, And we suppose only that all these numbers are non-negative. I will not even write it. And also pi plus qi is never 0. So I do not want that pi is 0 and qi is 0. This will give me something which you don't need. You understand? Yes. Now here, I write a fraction. The denominator is a number, m, times the product, let me begin with the sum, times the sum of all pi's and qi's, and times the product of all factorials. Such an integer. So the whole thing will be rational. And here I write plus minus, and then the following commutator. I use some notation which also should be, I write c to the power p1. I will explain what it means. Then eta power q1. And up to c to the power pm, eta to the power qm. This is the sequence of commutators. Now, what does it mean? C, k, at ck something. This, by definition, means that we apply, I can write add c to the power k to zeta. That is, we take zeta, take commutator with c, k times. This requires an explanation. And to give this explanation, I need to say that first, there are two possibilities. Either qm is 1, then no other conditions, or qm is 0, then pm is 1. Now it sort of makes sense. In this case, it will be c to the power 1, n to the power 0. I regard it as c. You understand? So this is the formula. It can be found in all textbooks, and actually the proof is sort of short. It is clear that what do we need to do? We need to check that yes, that the exponential of this will be the product to exponential. So it's sort of can be done. I will not do it. Written in many books. If you are not lazy, you can find it on the internet. Everything will be okay. But now let me say why I say that this formula actually is not, how to say, too useful. Look. Imagine that somewhere in the middle of this formula you have c to the power p, eta to the power q. So we have pq as pi and qi, but we can achieve the same. If instead of this, we can use the brackets p 0, 0q. So take pi is p, qi is 0, well, pi plus 1 is 0, the same. But this is not all. Certainly you can also write p prime 0, p double prime 0, 0q, and you can insert something here. So actually, it is very clear that in this sum, there are many, as children in intermediate schools say, like terms. And if I actually did this for your pleasure or something opposite to this, I took this formula and wrote all the terms which have combined degree in C and eta not more than 3. 2 lines in my notes, but actually there are only 3 terms. So they should be combined, then you know, you can certainly use the Jacobi identity and everything. So this formula has, how to say, good theoretical meaning. You see how it is expressed, all the algebraic properties of this expression, like rationality, so you can see that this is a rational function, rational series. So you can apply it not only over real complex numbers, but over any field of characteristic 0, because any field of characteristic 0 happens to contain Q fields of rational numbers, and so on and so on. Now, again, if you look at different sites of the internet, you can find the beginning of this formula, several first terms with their coefficients. Actually, how to do this? It is sort of an easy elementary problem. Imagine that the exponential is the real life exponential. It is true if you have the Lie algebra of matrices, if you have any subalgebra of this algebra, which actually is everything according to the Adot theorem over a field of characteristic 0. But actually, there exists a very direct algebraic way how to deduce what I'm going to say from very simple algebra not involving an analysis. So, suppose that x and y, whatever they mean, are 2 non-hermetic variables. So xy is not equal to yx. And we write this e to the power x times e to the power y is e to the power something mysterious. Now, if you have some expression for this, you simply can compare the series and it will be all okay. This is the way how actually the whole formula can be proved. Let us try to do the very beginning. This, you remember, x and y are non-hermetic variables. Suppose that we write, this is 1 plus x plus, and so on. Right? I hope so. Multiply. It will be 1 plus x plus y, right? Plus xy plus x squared over 2 plus y squared over 2. And I don't write the terms of degree more than 2. Is it right? I hope so. Now it is an exponential of what? If I write e just to the power x plus y, and x plus y do not commute, I get what? I get 1 plus x plus y. This sounds okay. Plus, however, the square of this divided by 2. It is x squared over 2 plus xy over 2 plus yx over 2 plus y squared over 2. What is the difference between the two? Only here, right? And to get this, I need to add to this also xy minus yx divided by 2, right? Very interesting. This is the commutator. Which means that if I, instead of this, take this. Minus actually, and subtract it. Then at least in degrees 1 and 2 it will be okay. Certainly, if you want to compare the cubic part, the terms of degree 3, again you will not have the same. You do more or less what I did. Only it is longer, it is boring, whatever. And the result is that this is up to, so this is degrees 2, that e to the power x or y is e or x plus y minus 1/2 xy, and some terms of degree 3. We don't have much choice. What are the terms of degree 3? This is the commutator of x with x, commutator x and y, not of y with x, commutator x and y. And this is what we get. You should add 1/12 of this and subtract degrees this, and this equality holds in degrees 0, 1, 2, and 3. In degree 4, certainly if you want this, you need to add something else. In some site, maybe Wikipedia, maybe somebody else, I saw a formula with 5 terms. Such a good fraction with 4-digit denominators. Yes, probably people know this formula up to some place, so they need a whole book to write it. Yes. So this is all I want to say about this formula. So the important thing is that actually many theories follow from this. That actually we can reconstruct. Certainly we need to prove that the series converges, something like this. It is so. It's very much converges for every x and y. So you see sort of explicitly, in some, how to say, semi-explicit way, that yes, the multiplication in the group is fully determined by the commutator in the Lie algebra. Questions? Again, you think that that last time you gave it 2 small questions and you think this is so. Well, up to you. Good. Dale. Maybe Dale. Dale. No? No. Dale prefers not to work today. Understandable. Good. So, from now on, yes, I do not mention such a thing as a Lie algebra. Maybe just for our results show that we need to undertake a serious study of algebraic properties of Lie algebras. Because something we know, this formula shows this in particular, something we hope to be true, that actually all problems, geometric, analytic questions about Lie groups, somehow can be resolved in the context of pure algebra, or the algebra of Lie algebras. And I begin studying Lie algebras. You have a portion of my notes. Actually, I have more. I will send them to you. The first section of my studying of Lie algebras. So Lie groups, please, if you have something about Lie groups, ask now. Because from now on, I don't know what it is. Yes, but I do know what Lie algebra is. By the way, when I speak of Lie algebras or representations of everything, at least up to some moment, I mean the finite dimensional case. So the Campbell-Hausdorff formula doesn't work in the infinite dimensional case. And many other things. In the infinite dimensional case, there are Lie groups, there are Lie algebras, but the relations between them are sort of loose. Every Lie group, infinite Lie group has a Lie algebra, but to say it is not true. The simplest possible examples of infinite dimensional Lie algebras don't correspond to any Lie groups. Yes. So the theory remains infinitesimal and has no globalization. It's still important. So let us establish some terminology. Lie algebras, you know what it is. Now, a representation of a Lie algebra. Can I use this term? This means that we have a vector space, as I said, finite dimensional, and the algebra is also finite dimensional. The ground field is R or C, but usually it is either true only for an algebraically closed field, then it is C. Either it is for any field of characteristic 0. Finite characteristic is a very different theory. Representation. This means that we have a vector space, we have a Lie algebra, a vector space, and for every element of the Lie algebra, we have a transformation, endomorphism, not automorphism, endomorphism in the vector space, and the commutator identity holds. That is, if you have two elements of the algebra, then their commutator in the Lie algebra corresponds to the commutator of these two endomorphisms in this space, AB minus BA. If A corresponds to C and B corresponds to eta, then AB minus B corresponds to the commutator of C and eta. In other words, we have a homomorphism of the Lie algebra, given the algebra, into the Lie algebra of matrices of endomorphisms in a vector space with the usual Lie algebra structure. Okay. Now I have to begin this algebraic investigation of Lie algebras with the case which may be not the most important, but still it is natural to begin with this. I mean now nilpotent Lie algebras. Do you know the word nilpotent? Nilpotent means zero power, power zero. Nilpotent operator in the vector space is simply an operator. Say some power of this operator, you can apply some time, is zero. Stupid question. What is the power? If we have a nilpotent operator in a space of dimension 10, then it is zero, definitely. Its which power is zero? 10th power, yes. Maybe less. But 10th power is zero. Why? You know, nilpotent, all operators have matrices. Again, I say something and you will tell me whether any explanations. If you have a nilpotent operator, then in an appropriate basis, it will be strictly upper triangular matrix. A matrix whose entries below the diagonal and on the diagonal are zeros, and above the diagonal they are something. It is very clear that when you take the power of this operator, then this domain of non-zero entries shrinks and shrinks and shrinks and shrinks and becomes zero as soon as you reach the order of the matrix. Yes. Now, why so? I want to say that all operators have eigenvalues, but nilpotent operators, you know, all eigenvalues are zeros. Why so? Because when you take a power, then eigenvalues also are raised to the same power, right? So the eigenvalues of your nilpotent operator have this property that if you raise them to some power, they become zero. But no number will become zero if it is not zero itself after raising to any power. So all the eigenvalues are zeros. Then you can take what you call the normal Jordan form, and it will be upper triangle. Low triangle, this depends on how you prefer to write it. And what is important, that 0 is 0. Actually, all operators have eigenvalues, but in the real spaces, operators can have complex non-real eigenvalues. So actually this procedure of diagonalization of anything can fail when you consider the real case. But 0 is 0. If all eigenvalues are 0, they are very much real. So this is nothing. So this we have this definition from the elementary linear algebra. Now, we have a Lie algebra in its representation. It is called nilpotent, you will be surprised, if all the operators which are provided by these representations are nilpotent. That's all. You have something to...
No.
Any objection? No. That's all. Now, a Lie algebra is called nilpotent. If what? If its adjoint representation is nilpotent. That is, if you remember that one of the representations of the Lie algebra, which is called adjoint representation, is the representation in itself. An element of the Lie algebra, the corresponding endomorphism, is the commutator with this element. And this is what I wanted to say. Nilpotent Lie algebra, yes. Now a stupid question, and it is so stupid that I even, for your entertainment, yes, wrote an exercise. What is the relation between these two nilpotencies? And the most stupid thing which can be said, but it is correct as most many other stupid things. First, that a representation of a nilpotent Lie algebra is not necessarily nilpotent. And second, if a representation of a Lie algebra is nilpotent, then it is not true that the algebra is nilpotent. The first is especially obvious, is an exercise, but take one-dimensional Lie algebra is always nilpotent. What else? It is zero commutator. But think of its representation. What is this? So on the first glance, the relations between nilpotent Lie algebra and nilpotent representation is not so direct, but actually it is direct, because there is a proposition, a theorem, which is also written in my notes, that if a Lie algebra has a faithful nilpotent representation, then it's nilpotent. The question arises, what is faithful? Faithful means kernel is 0. I don't think you should ask me about the origin of this strange terminology, but it's called faithful, which means that no non-zero element of the Lie algebra produces a zero endomorphism of the space. Otherwise, if it is not faithful, there is such a thing as kernel. So this homomorphism of G in the GLN, say 0, R, may have kernel as any homomorphism. And this kernel is an ideal in the Lie algebra, and faithful means that this kernel is 0. So proposition. Let me spend a couple of minutes on proving that, and then we will do something more interesting. So proposition. If a Lie algebra G has a faithful nilpotent representation, then this is not potent. This means that if there is some faithful nilpotent representation, then also the adjoint representation is nilpotent. So why? Consider the adjoint representation. So my representation which is faithful is rho. Rho. A faithful representation. Now let me consider such a thing. I take two operators, A and B, just operators, and I take K, B. So I take the following thing. I take B, commutator with A, again with A, and so on. K times. What is this? If K is 1, then it is AB minus B. If K is 2, so we need to multiply this by A from the left, then from the right, and then take the difference. It will be the following. It will be A squared B minus 2 minus 2ABA and plus BA squared. If it is not so, then I don't know what to say. Yes. Then for an arbitrary K, simple induction, and actually this suggests the following formula. So add A to the power K B is the sum, negative 1 to the M, M 0 to K. Now A to the power K minus M. Oh, no. K choose M. A to the power M minus K. B A K minus M, right? To the power M. This is the formula. Now look at it. Suppose that A is an nilpotent operator. If A is an nilpotent operator, then this is 0 for sufficiently big K. Because either this or this, if K is very, very big, then either this or this will be 0 for any M. Then the whole thing is 0, right? So we see that if A is an nilpotent operator, then add A is an nilpotent operator. This resolves our problem, because if we have a faithful representation, then for any non-zero element of the real algebra, we'll give you a non-zero element, non-zero endomorphism. So actually, we can apply this. The effect is right. Now, all this is not very, no, it is interesting, but not very important for us now. There is an important thing. The main result in the theory of nilpotent Lie algebras is usually attributed to Engel. Theorem of Engel. Engel is a German mathematician, and when Lie, Norwegian Lie, who didn't speak proper German, became a professor in Leipzig, so in Germany, he needed somebody to help him in everything, including his mathematical research, his lectures and everything. And Engel, who was then young, was actually an assistant of Lie. Was necessary because Lie could not survive without this kind of assistance, because of the language, mainly. And then Engel, so he was a student of Lie in some sense, and then he became a famous mathematician himself. And this theory, which I'm going to formulate and prove now, actually had been now published by Engel wrote a letter to somebody, I don't remember whom, with this theorem and with some idea how to prove it. And then Engel also had a student who wrote his dissertation, which was actually the rigorous proof of Engel's theorem. Still theorem, and even I simply don't remember the name of the student, and this theorem is attributed to Engel. This is right, because certainly Engel understood that this should be true, and why. So theorem. There are two statements of it. One is useful, and one is something which is convenient for proving. Useful statement. Suppose that we have an nilpotent representation of some Lie algebra. R or C. I write R, but C certainly will, but actually any field of is 0. B, an nilpotent representation. No, let me write here. This is better. I write V. So V is the space of representation. And I like this notation because it is not, it has no explicit reference to the field. So V is the finite vector space where this representation works. Then there exists a sequence of subspaces such that for every C in G, if you apply the corresponding endomorphism to Vi, you will fall into Vi minus 1. In particular, what happens if you apply this to 0? Then to V0. Then you get 0. Well, I didn't write that V minus 1 is 0. It sort of suggested by this notation. Yes. If you apply it to V, to whatever it be, you will get something from Vm minus 1. There exists a different way how to formulate it. And I will say this to you, and you will say that yes, 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 or why. You remember that every nilpotent operator at all can be given by a strictly upper triangular matrix. With some basis. Basis should be chosen for that. And now I want to say that there exists one basis in V, one for all, so that for every element of the Lie algebra, the operator rho of C is represented by an upper triangular matrix. It is very much clear. Choose a basis in V in such a way. First, take basis in V0. Stop here. Then add to it a basis supplement it to a basis in V1. So take a basis in V1 factorized over V0 and then lift it to V1. And so on. Then certainly the matrix of every operator with this property will be with respect to this basis, upper triangular. Yes. By the way, this theorem can be applied also to the adjoint representation. Suppose that we have, so V is G. So we have the following. And here, no equalities. right? Such that the adjoint representation, well, forget about representations. If you take any element in G and take its commutator with any element of Gi, you will get an element of Gi minus 1. So this gives you a structure of any nilpotent Lie algebra, which means actually that a nilpotent Lie algebra after this adjoint representation becomes embedded into the Lie algebra of upper triangular matrices. But I don't want, this is not what I wanted to say. Look at G0. What about commutators of G0 with all other elements of G? They are zeros, right? With the kind permission, this means that G0 is central. So in particular, this shows that every nilpotent Lie algebra has non-trivial center. Maybe at some moment useful. Now let us consider the proof. Unfortunately, I have 8 minutes. Maybe I will have to finish the proof. Proof is elementary and simple, but still, I need to do something. So first of all, this angle theorem, this is the angle theorem, depends on a certain lemma. And in the reasonable books, this lemma is what is called Engel's theorem. Because it is it's actually what we need to prove. And it is the main property of nilpotent representations. So again, suppose that it is a lemma, but actually this lemma again is called it's called Engel's theorem in reasonable books. Suppose we have a nilpotent representation. Then there exists a non-zero vector in V such that rho xc of V is 0 for every xc. So the kernels of these operators have an intersection. So what? Do you believe that this, certainly this is implied by my previous result theorem, because any vector in V0 will work. V0 is not zero space. But do you believe that this implies that theorem? Certainly. How to do it? How to deduce angle theorem from this lemma? Begin with V0. Take for V0 what? The space of all vectors V with this property, including 0. Right? It is a subspace. At least V0 we have. Where to get V1? Take the quotient. So V0 is a subrepresentation. Certainly if all the pairs are 0. Take the quotient of V over V0. It is again a representation of G in this space. And what? And it is also nilpotent. In this respect, no changes. I didn't say this, but it's impossible to say everything. All sub-representations, quotient representations of nilpotent representations are nilpotent. This is very obvious. So take V over V0 and apply the same lemma to it. Then you will find a subspace in V over V0, which is annihilated by the representation. Take the inverse image of the subspace in V. It will be V1. And in the quotient, the image of any element of this subspace is 0. After the lifting, any element, if we apply an element of the algebra to the element of the space, we will get an element of V0. You factorize over V0. And so on and so on, V2, V3. Every time the dimension becomes bigger and bigger and bigger, since V is finite dimensional, we at some moment reach V. Now how to prove this lemma? Very much unfortunately, I will not be able to finish it today, but I will say the main thing, and I will give additional explanations next time. Induction. What else? We apply induction with respect to the dimension of G. If G is one-dimensional, then what is the representation of a one-dimensional Lie algebra? It's just one operator, right? We take some basis element in this one-dimensional space, and it gives operator on other elements of this algebra, the same operator times numbers, right? So basically, a representation of a one-dimensional algebra is just one operator, nilpotent, because nilpotent representation. Nilpotent operator always has a kernel. This is your vector V, done. Now, how to pass from one dimension to another dimension? And for this purpose, we need a sublemma. A very simple actual statement. I probably will not prove it today. But I say this. Every nilpotent Lie algebra has an ideal of dimension 1. My friends, from Engel's theorem, certainly this follows. Just take any space between Gm minus 1 and Gm. It will be an ideal in G. So actually, nilpotent Lie algebra has ideals of all possible dimensions. But it follows from this theorem. So far, we don't know it. So we need somehow to construct an ideal of codimension 1. So dimension is dimension of G minus 1 in G. After this, it is basically nothing. So if, let me show to you this part of the proof. So the dimension 1 is obvious. Suppose that it is true for some dimension, and we find an element. We find an ideal of codimension 1. My representation is also representation of H, right? So there are vectors which are annihilated by H. We have a subspace. We have a subspace W in V such that non-zero, such that rho V, G, no, last attempt is correct, rho H, W is 0. Now, take any element C in G minus H, so any element of G which is not in H. Then we can easily prove, I don't have time for this today, unfortunately, that rho C at least, that W is invariant with respect to this rho C. This is 1 second. And this becomes a nilpotent operator in some vector space. And it has a 0 vector. And this gives you all. The 0 vector will be 0 with respect to C, also 0 with respect to H, and then to 0 with respect to everything. This is how it is proved. I have 8 more seconds, but it is not enough to do for anything. Maybe question for 8 seconds. Page. No. Let's see you next time.